Hi everybody, I'm James Powell, and today we're going to try rewriting the itertools module in Python from scratch. I don't know if we're going to be able to do that in 30 minutes of time. In fact, there's a lot there. But we're going to show you what's so interesting about the itertools module. We'll talk about why we like the itertools module so much, and we'll see what the really important reason behind embarking upon this very interesting crusade might be. But first, our goal is to talk about how we would go about writing itertools from scratch, and maybe even why we'd want to do that in the first place. I want to dive right into it, and so in order to do that, I will share my screen with you. Here's the rules of the game. I want to rewrite the itertools module, a module that I use all the time, maybe in the top 5 modules that I import in any given Python code, including my analytical code using NumPy and Pandas. Well, I want to rewrite it from scratch, such that I use no imports, but allowing that some of these pieces can be written in terms of each other, but requiring that I write a faithful implementation that ties out to the actual itertools module. And so, in order to get started with such a challenge, I need to understand what's in the itertools module. So if we take a look at the contents of the itertools module, well, it's a bunch of these things that are callables, maybe they're functions, maybe they're classes. They seem to be written in C. They have some very interesting names with them. And it turns out that they're all iteration helpers. We are familiar with iteration helpers because in the built-ins we have 2 of the most useful iteration helpers that we'll use, enumerate and zip. And the itertools module says, well, iteration helpers, what a great idea, let's do more of them. And so the itertools module contains a bunch of these things that help us do iteration better, either by generalizing approaches that are related to iteration, like the slicing that you have with the square bracket syntax and a colon is generalized by islice, or chaining, which you can do in a variety of different ways. Different data types support different ways to combine each other. Well, you can do that with .chain. We can broadly take all of the things that are the itertools module and we can categorize them into certain categories. And the categories might be combinatorics. So we have permutations that computes the permutations of some data, combinations and combinations for replacements, which do combinations with or without replacements, product, which computes the Cartesian product, an operation that comes up all the time, because when you think about something like a pandas multi-index, it's oftentimes you're computing it from the Cartesian product of 2 different layers. We have filtering type operations like itertools.compress, which selects whether it wants to keep or remove values based off of a mask. Or drop while, filter false, and take while, which instead of taking a mask of true-false values, take a predicate, which they use to compute that mask. Drop while, skipping all the items until it finds the first true and then giving you all of the remainder. Take while, doing the opposite, taking items until the predicate is false and then halting. And filter false, which is very much like our built-in filter function, except instead of taking the items where it is true, does the opposite, takes the items where the predicate is false. We have ordering operations, chain, which allows us to chain together multiple iterators so we can iterate over one and then the next one and the next one without having to concretize them or without having to find some sort of unpacking syntax or some syntax that allows us to directly add them to each other. Cycle, which allows us to repeatedly cycle over an iterable. Pairwise, which personally I think is a little bit hokey because there's a better choice than pairwise, but you get overlapping windows of a particular size of size 2. Repeat, which allows you to just continuously repeat a value. Islice, which allows you to take that slicing operation and generalize it to something that might not be concrete. You skip some values, you take values until some stopping point, and you step by some stepping. Or zip longest, which works like our built-in zip, except if one of the things that we're zipping is shorter than the other, well, we have a fill value that we can fill in. We don't terminate early. We have some computation-related things, accumulate and star map, which are very closely related to the built-in map. Accumulate is star map actually can be replaced by map these days. They added one additional API or one additional approach that you can use with map that allows us to not really have to work with star map anymore. Basically, that's just applying a function to a number of iterables by zipping up their contents. And accumulate, which used to have a very similar function in the built-ins in Python 2. Accumulate is basically functools.reduce, except you get each individual step of that reduction. If you think of functools.reduce as a fold, well, accumulate in the itertools module is a scan. We also have some miscellaneous. Count just counts from some starting point to infinity. Group by allows you to group things by some predicate, and T is very interesting and incredibly useful. It creates transparent buffered copies of some iterable, and it's something that we'll definitely need to use if we're working with some non-concrete data like a generator. Well, our goal is to re-implement all of these and to re-implement these in pure Python to whatever degree we can. And it turns out that some of these are very easy to implement in pure Python. Count is just an infinite loop where we're just yielding the value over and over and just incrementing by one, or if we want to take into account the step, increment with the step. Our goal in re-implementing the itertools module is to make sure, to the greatest degree possible, we are faithful to all of the keyword arguments that we have. So we might say, instead of just this being +1 and we ignore this step, or we ignore the start, we want to take that into account. And so here we can see, in the most basic case, our implementation ties out. Well, we want to tie these out a little bit more formally than just printing a couple of outputs to the screen. That sounds like a unit test, but that unit test of just these 4 items from the head of the official count and our version of count, I don't know that that's good enough. So what we'll do is we'll make use of the hypothesis library in order to write really nice PyTest tests. But how do we actually test count? This is an infinite sequence. We're going to allow ourselves some certain assumptions for how we perform this test. So what we're going to say is, if the first n values, maybe the first 100 values, tie out exactly, then this counts as a pass test. Because how do we make sure that count doesn't give you a really weird value, 1 billion values in, or 1 trillion values in, or more values in than we have memory for? Well, probably because it probably wouldn't. It's kind of reasonable for us to say, look, if the first 100 values tie out, probably everything ties out. And in truth, this is probably good enough for us to make certain assumptions, or to tie these out if we're not including the performance. Note that our pure Python implementations of the itertools module will not tie out from a performance perspective with the official implementations, which are largely written in C, and as a consequence have access to certain tricks that we just don't have access to in pure Python. Well, I said we wanted to write interesting and useful tests using the hypothesis library. And when you hear hypothesis, one of the things that you think about is property testing. We could definitely write property tests for everything in the itertools library, but typically we're writing property tests because we don't want to write an oracular test. We don't want to write a test that says, here's the expected value and the actual value. I compute the expected value by asking some oracle. What's the answer supposed to be? Because in truth, in most cases, we don't have an oracle that can affirmatively tell us this is what the answer should be that we can tie out. We either have to pre-compute something and say, that looks right if I spot check it. Well, in the case of re-implementing something, we definitely do have an oracle, the oracle being the official implementations in the itertools module. So most of our tests will look something like this. We'll take our count implementation, we'll set up a test in PyTest, and we'll say, does a.count match b.count with the start and the step randomly selected using hypothesis algorithm for trying to find things that might be on the boundary between correct behavior and incorrect behavior. And one thing I really like about this is, when you look at the code like this, you can't tell which one is A and which one is B, which one is the official itertools module and which one is my itertools module. Well, I'll give you a hint. In fact, it turns out that the itertools will always be A and my implementations will always be B. But I kind of like that you can't quite tell, so it really is a very faithful attempt to tie these two out. Well, if we run this and we see, does our count tie out? It does. Fantastic. We are able to tie out count. It wasn't the hardest of them to write. We're going to need to make certain assumptions, though, in our tests to get these tests to be possible to write and to pass. And so, for example, if we look at something like itertools.product, our itertools.product here is a recursive formulation. And if we're looking at more than 1,000 elements in the window that we're trying to create, well, we're going to hit the recursion error. But in truth, are you using itertools.product with something that has 1,000 elements? And in truth, are we concerned about that particular level in our first pass of the reimplementation? Not really. So we'll make some reasonable assumptions like that the iterable has only a particular size, it has a maximum size associated with it. Maybe we'll make another assumption about the parameter, the repeat parameter. Note that itertools.product takes multiple different iterables. So we'll say it takes at max 10 iterables, which are at max 1,000 elements in size, and it's going to ask for that repeat parameter at max 10 times. We could, of course, bump this up an order of magnitude. It'll just slow down the test, but I don't think it's the case that that will give us any ability to disprove the correctness of our code any better than if we make these assumptions. So we'll make those assumptions and see, does our implementation of product tie out? Ooh, it takes a while for this one to run. You can see some of our implementations are just not particularly fast, but if we were to limit a couple of these aspects just a little bit more, we might see that we'll limit this here, we'll limit it here, and we'll limit it here, and we'll see if that's enough to get this to tie out in the time that we have allotted. Hopefully, okay, there it does pass, and then maybe we'll bump that up just a little bit more. So we have an implementation of product. There are some details of the official implementation that I think we should just flat out ignore, in part because they're things we can get to later, and they're just not that interesting. I'll give you an example. itertools.islice has a signature very similar to the typical slicing signature, which means if you pass one entry, then that is the stop. If you pass two pieces of data, or at least two positional arguments, then that's the start and the stop. If you pass three, it's the start, the stop, and the step. And if we think about trying to tie that out in our code, we'll end up having to do something kind of silly like this. Also, you can pass none of some of these values, so we'll have to have a lot of is-none checks. Personally, between you and me, I think that we can simplify some of the API aspects. We can cover those later. So in our tests, we'll just test passing all of the arguments. We won't test, oh, does this work correctly if you don't pass this argument, if you do pass this argument, if you pass these arguments in this fashion, because we can always come back to that and test that, and we may need to make small tweaks, but those tweaks won't be about the overall correctness of our implementation. They'll just be about the API that we're presenting. There are, however, some details that we'll want to consider that are functionally related. I'll give you an example. If we are doing itertools.cycle, and we're doing a cycling of some concrete iterable like a list, well, it should give us 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Well, what happens if we append a value to this structure right before we go to the next value? Well, in the official implementation, has it taken a reference to this data? Has it made a copy of it? Has it dumped this into a list and made an implicit copy? I don't know. In our implementation, we just keep yielding values until the original list is empty. And so in this case, we should see some value. Well, thankfully, our implementation does tie out with the official implementation. And we could think another question could be, when you're out of values, and then you append a value, what happens? So let's actually get ourselves out of value and into the cycling behavior. And you can see both ignore additional values past the end of the first cycle. And so those kind of details we might want to tie out as much as possible. We won't write tests for these, though, because we can pretty much write these tests in a fairly uniform fashion. To write in what happens when we mutate these is going to ask us to extend those tests very slightly. It won't be that difficult for us to rewrite all our tests to also include a test case for this. But I think just the simplest tie out with all of the arguments passed is a very good starting point to make sure that we have good, solid implementations. There are some behaviors that actually probably should be part of the specification of how things in the itertools module work that I think that we will not care about tying out, even though they may be relatively interesting from a perspective of a user. It's just that from a perspective of our first pass implementation, they're not going to add that much richness to our approach. I'll give you an example. If we look at something like itertools.combinations, if we ask for combinations of size 0, we know what the answer is. The answer is there's always one combination of size 0, which is an empty tuple. And if we ask for combinations of some other size, well, it's just some number of elements from the combinations of that size. Well, it turns out that combinations eagerly consumes the iterable that it's passed. And so you can see, even though it knows that the answer is always going to be an empty tuple, it still has gone in and consistently consumed the entirety of the values from the generator, even though it didn't need to do that. Well, we could say that this must be part of the specification, and we could argue whether this is the right thing to do as part of that specification or not. Personally, I can see why they chose to do this. This means that the itertools.combinations implementation will always entirely consume whatever you pass it, no matter what, so you don't have a hidden modality there. But other people might argue maybe we shouldn't be pulling values from a generator unless we're certain that we need them. From our perspective, it probably won't matter that much, because in our implementation of combinations, eagerly pulling in all the values and consuming all the values versus only consuming them if we know we need to look at them really just means moving this one line of code from here down to here. And in truth, I don't think that's altogether that interesting. Well, it turns out that our implementation of combinations does not work. And the reason it doesn't work is we're going to implement combinations in terms of permutations and pairwise, which I think is fair, as long as we don't implement combinations in terms of the official permutations of pairwise, but rather in terms of our personal reimplementation of pairwise and permutations. And so here we can see an attempt to tie out the behavior of itertools.combinations given an implementation of itertools.permutation, which itself requires an implementation of itertools.product, and an implementation of itertools.pairwise, which itself requires an implementation of itertools.t and an implementation of itertools.islice. So it turns out that some of these end up creating a lot of additional work. I think that if we can get combinations to work, then along the way we've gotten a lot of other things to work. And so let's run this code and see, does our implementation of combinations work out? Yes, it does. And this is a very, very good sign that our implementation of islice, t, pairwise product, and permutations probably also tie out correctly. But I just showed you pairwise, and I didn't make a slanderous comment about its hokiness. What is wrong with me? Every time I talk about pairwise, well, every time I talk about itertools, well, every time I talk about generators, nwise, our dearest friend, always comes up. And we might wonder, are we trying to re-implement the itertools module in order to do something related to nwise? I don't know. nwise, as you know, is our generalization of what it means to do a pairwise operation. Instead of looking at overlapping windows of size 2, we look at overlapping windows of size n. So we look at windows of size 3 or 4. And these have to be fixed size windows, very similar to, say, a pandas.rolling when you don't give it a TS offset, when you give it just a fixed integer. Well, when we write nwise, what's interesting is it leads us to writing things like nwise longest, which is basically nwise, except when we run towards the end of this, we fill in with the fill value. We just swap out the zip for a zip longest, which then leads us to write first and last, which are iteration helpers very similar to enumerate. That is to say, whereas enumerate gives you the index of something and the value itself, first and last just give you a true false of are you the first in the sequence or are you the last in the sequence, the first n or the last m. And we can write these by combining small building blocks from the itertools module. I think a very interesting test would be, can we re-implement nwise longest, first, and last using our custom implementations of all of the building blocks from the itertools module up to and including a re-implementation of both zip and enumerate, because I think that's fair game for us to try to re-implement. And it turns out we can definitely try. Here is an implementation where we have re-implemented zip, including the strict flag. We have re-implemented islice, including a little bit of the different arguments that we can pass it and the different ways that it parses these positional arguments. We have re-implemented enumerate in terms of zip and in terms of count, which means we have to re-implement count. We've re-implemented t because we need that for our nwise. And I lied to you slightly. I think it's fair for us to have one import. That is to say, when we implement t, we need a first in, first out for the transparent buffers. We need to say, oh, if there's some buffer data, give me the element from that buffered data. Don't give me any elements from the live data. And I think that we want this to be first in, first out. The first thing that gets added to the buffer is the first thing that we pop out. So I think we want to pop left. We could do this with the built-in list. It's just the performance would be terrible. This is just trying to eliminate something like a del of x's of 0, which is just very poor performance. So I think here we can argue that this one singular import is fair game. But we have an implementation of t. We need an implementation of cycle to make this all work, and we need an implementation of chain to make this all work as well. And probably as we're going to do chain, we should do chain from iterable. We need an implementation of repeat and zip longest. So we have an implementation of zip longest and repeat. And together, we can create some very nice tests that test, does the implementation of nwise using the itertools module and the built-ins tie out to an implementation of nwise using all of our re-implementation of those built-ins and things in the itertools module? Can we do the same thing for nwise longest? Can we do the same thing for first and last? And if this works, this will serve as a pretty decent tie-out for much of what we have in the itertools module. nwise works, NY's longest works, first works. Let's see if last works. Last works. Oh, our reimplementation of the itertools module seems to be off to a great start. Well, it turns out that I've done almost all of the work already. I have written a reimplementation of everything in the itertools module, and we'll be sharing all of this code with you as part of our session materials. I want to create a GitHub repository, including this, as part of plans for our next step in this project and our next session on this topic. If you would like to be a part of a very interesting open source project that we can all work on together, please share your GitHub username with us on Discord. We will add you to that private repo. It'll give you access to all of the code here and all of the implementations here. It'll give you an opportunity to maybe send me some pull requests to improve the formulation, some of which I did a little bit sloppily, some of which have fairly poor performance, some of which you might have a better way to just simply write. And I also have tests for every piece along the way. I'd love to have some of your contributions to maybe add additional tests, to test some of the other modalities that might exist in these, to test some of the other possibilities for if we mutate the thing we're iterating over midstream and see if they all tie out. Of course, I think there are some things that we'll just consider to be outside of scope, off topic completely, just because it's not that interesting to do a exact tie out with the itertools module, especially if the itertools module does some things that we might find questionable. But it turns out that there is a motivation for this overall. I'll tell you what it is. I actually don't want to rewrite the itertools module from scratch. Maybe it's useful for me to get a better sense of what the itertools module is capable of doing, for me to really think what do all of these pieces do and how are all the ways that I can mix and match them and reuse them. How is it the case that some of these might be re-implemented in terms of each other? And that could give me some guidance in my day-to-day work. But it turns out there's a much narrower and much more interesting problem that I want to solve. Here we have our re-implementation of count. And it makes sense for us to combine count with an isSlice. Let's do a count, and let's just skip the first things we're counting over. So we skip over 2. Here is an implementation of something that I call recount. This is count where it is not a generator, but rather a coroutine. We can send data back into it. And what we can send back into count is recount. Start back from 0. So when we go through the values of recount, we get 0 and then 1. And if we say, no, start over from 0 again, it starts over from 0. That could be useful. And then 1. And we could even say, you know what? Start over from 100. And it starts over from 100. What if we isSlice this? Is this going to work? If we try to isSlice this, then we'd expect, okay, it goes from 2 to 3, then we start over from 0, and it goes up to 1, and then it starts over from 100 and goes up to 101. Except it doesn't work. The itertools module is written for iterators. It's written for generators without send. The itertools module implementations do not implement .send, .or .throw. They don't implement any of the things that are useful for any sort of coroutine related approach. And I think in this case, it really makes sense for us to be able to slice a coroutine. In many cases, there may be some question as, is it really meaningful for us to determine the combinations without replacement or the permutations or the Cartesian product of a coroutine, which is a live computation that has been broken down into parts that we can feed partial inputs into? Well, it may not be the case that everything in the itertools module needs to have the coroutine functionality, but it's definitely the case that some things in the itertools module, under some very common circumstances, probably should have that behavior. And by rewriting the itertools module from scratch, it gives us a very nice starting point to rewrite the itertools module from scratch one more time, but this time to implement, where appropriate and where relevant, coroutine functionality. And so if we revisit what is in the itertools module, and we revisit the implementations, we could think, well, we have our count here. We have our cycle, which is going to be a part of our isSlice. This is how we wrote isSlice to tie out with the itertools module. All we have to do is change one line here so that it takes into account that this could be a coroutine and we can have more input coming in to allow our custom implementation to support everything that the itertools module supports, but also to be aware of coroutines to support what happens if we pass it not just an iterator, not just a generator, but something that can have data sent back into it. In fact, our implementation of the itertools module may be a very good starting point, a pure Python starting point for us to write not itertools, but coroutools, a library of helpers for working with coroutines, maybe even for working with pumped coroutines. Now, this is a first pass implementation, of course, because the performance of this won't be very good. But we can first sketch out how these should work. We can sketch out the semantics, get the pure Python implementation working, and then judiciously drop everything down to the C layer to retain the performance that we get from the itertools module, and we can have a much more generalizable itertools module. So if we're to go back to everything that is in the itertools module, in other words, in closing, what comes next? Where is this going to send us? Is this about throwing out all of itertools? No. It's about looking through what's in itertools and figuring out which of these parts probably should be coroutine aware. Which of these parts does it make no sense for them to be coroutine aware? I think for the combinatorics, I don't think that it makes sense for those to be coroutine aware. I'm not sure what it means to have a live function that's been broken down into parts and you find the Cartesian product of that. I think for the most part, all of these assume that they're going to concretize the iterable that they're passed. And in most cases, when you're concretizing the data that you're passed as the first immediate step, it probably doesn't make sense for this to work with coroutines. For filtering, I think it does make sense. I don't know that it's that useful, though, because you can think that if you have a coroutine, well, maybe you could do that filtering through some sort of comprehension syntax, except comprehension syntax, that is the generated expression comprehension-based syntax, also doesn't support send. So I guess actually, in truth, this is actually quite useful. We have some coroutine, and we're going to pass data into it, and we need to figure out how to filter that down to the data that we want to have come back out of it. Now, in all cases, when we're re-implementing these in the coroutine formulations, a very big question is, if we're skipping over a value, well, what do we send back in? Is there a fill value? Is there none? I think that's part of the exploration of the semantic of these items that we will need to embark upon in order to perform this implementation. But I think all of the filtering are probably in scope. For the ordering, chain definitely is in scope. We have a computation that's a finite number of parts. We do this one, this one, this one. Then we switch over to another one, this one, this one, and this one. We should be able to send into chain. Definitely in scope. Cycle, I'm not sure. Maybe you should be able to do this for the very first pass through and then forever after you're on the buffer. Maybe there's a modality associated with it. Maybe it's the case for things like cycle. Maybe we need to have something that's not quite cycle, but very similar to what cycle is trying to accomplish, that then gives us the ability to work with coroutines. Because I think here the semantics sort of make sense, but sort of don't make sense. Pairwise, maybe on one of the read heads for pairwise, it makes sense to support coroutines. On the remainder, maybe not. For repeat, this is about repeating a singular value, so I guess maybe repeat might be out of scope. For islice, definitely in scope, but we might need to litigate the semantics. For zip longest, I think so, but I wonder if you zip and then you send something into it, do you send it to each one of them? Could a zip and a zip longest supporting coroutines be like a forking where you send one piece of data into the thing and then it sends data into each one of the subsequent items? Some sort of redirection that redirects to both sides, kind of like T with process redirection at the shell. For accumulate and star map, I think maybe it makes sense. And for count, group by, and T, I think count is probably out of scope. I think for T, it is very interesting whether or not it is or isn't in scope, because if you have transparent buffering copies, I think you should be able to send data back into, but only back into the most live end. And what do you do when you're trying to send data into the least live end? Maybe you buffer that. Well, actually, that's interesting because you've already moved past that, so maybe you error out. Maybe in some cases, it's the case that you implement these, but you create errors where you say, look, it doesn't make sense to try this behavior to send data back into part of the T that's only reading from a buffer. And so what we'll say is we're not going to allow that. But for other cases, it may make sense, and we'll implement that. Well, here's what I want you to do. Share your GitHub handle with us on Discord, and we will add you to the private repository that we're creating that includes all of the code that I've written so far and will be the starting point for writing coroutools. Sign up for our newsletter because we will do another session in the near future where we're going to take all of the work that we've done here and we're going to start thinking through each and every one of them. Does it make sense to make this coroutine aware, and how do we do that, and what does the implementation look like? I've already gotten started on that. I already have coroutine implementations for about a fifth of these. Finally, if you like this session, please do let us know on Discord. We love to hear feedback from you. And then finally, if you'd like to try this yourself and reach out to us and ask us, is this the right approach to take? Is this how you would do this? We would love to hear from all of you. But whatever the case is, I hope that you'll join us for our upcoming session, which we'll announce shortly, about rewriting coroutines, maybe not from scratch, maybe writing it for the first time. But otherwise, thank you all for joining us, and I'll see you all next time.